Today's video is a recording of a talk that I gave at the FairLawn Amateur Radio Club earlier this year. The title of the talk is The Basics of Oscilloscopes and Their Use in the Ham Shack. This video is a recording of Part 1, The Basics of Oscilloscopes. It also talks about how to use them and some of the fundamental differences, advantages, and disadvantages between analog and digital oscilloscopes. Be sure to visit some of the links that I'll link down below in the video description that will take you to the FairLawn Amateur Radio Club website, as well as their YouTube channel, which features additional videos of other speakers that they've had at their club meetings. So sit back and enjoy and learn a little something about oscilloscopes.
Brad, here he is. Okay, back to you. Thank you.
All right, our presenter tonight is Alan Wolke, W2AEW. He's a good friend, and he was willing to come out here and give us a nice demonstration of oscilloscopes in the ham shack. So I'll turn over to him.
So we'll see how I do with the microphone, otherwise I might have to put it down. Can you hear me okay with this?
No.
Bring it up a little bit better? Is that better? Okay. So anyway, that's me. I'm actually the technical coordinator for the Northern New Jersey section of the Hudson County Division, the ARRL. The way to get a hold of me, just my call sign, W2AEW@ARRL.net. It's an easy way to get a hold of me. I also have a YouTube channel, just youtube.com/mycallsign, and we've got a little over 10 million views on that. So a lot of what I'm going to do here are things that I actually have done videos on in the past. So if you want to go back and review, you can watch the video from tonight, or go back and watch some of the other individual videos of what we've done. So first question before we start off, how many folks have got oscilloscopes in their ham shack? Now be honest, how many of them are sitting under the bench collecting dust? That's what I thought. Because they don't know how to use it, or afraid to use it, might blow it up, not sure what to do, so we're going to try and clear some of that stuff up tonight. Any questions that you have, certainly let me know. That's the reason why we're here, is so you guys can learn. So not just to hear me go through the slides. I apologize right away for any potential spelling errors you might see. I was editing these slides up until last night. Okay, so our agenda tonight, talk about the basics of an analog oscilloscope, what it is, how it works. I'm a firm believer, if you understand how something works, you can always use it better and use it more efficiently. So we'll talk about the display characteristics, the vertical, horizontal, and trigger sections of an analog scope, what they do and how you use them. We'll talk about the basics of a digital oscilloscope and compare and contrast the analog scopes and digital scopes. Talk about when an analog scope might be better for you, or a digital scope might be better, or when it doesn't really matter. Okay. And then we'll talk a little bit about probes, an often misunderstood topic about why we use probes and things like that. So we'll talk about probes, why we use them, how to use them properly. And then we'll get into a couple of applications of using an oscilloscope in a ham shack. We'll do a little TDR demo, actually measure the length of coax using an oscilloscope, pretty cool. Maybe monitor the output of a little RF transmitter I've got here, my little ICOM 703. And even measure some unknown inductors and capacitors. So a couple of interesting little things that we'll do, some potential applications where you can use a scope in your shack. So first off, let's talk about the old cathode ray oscilloscope. And these are the old analog scopes that have got a CRT. The CRT's got radicals that kind of have divisions, both vertically and horizontally. And basically the way this works is they're just like the old TV tubes. We're shooting an electron beam out of the back of the CRT up to the face of the screen. That lights up the phosphor. And then the scope is really just steering that beam around. And the controls on the scope are really just there to steer it around in a way that is useful for us to make measurements. Okay, so we're going to cover each of the various sections in the oscilloscope and how it controls what's going on the screen, so you can really understand what it's doing. So the first thing we'll talk about is the display system. There are controls just for the display. And those controls are things like the intensity and focus. Those are pretty self-explanatory. Obviously, how bright we're going to make the screen or the trace, and how clear and how crisp it is. And these don't automatically focus like your cameras do. You often had to adjust that. And sometimes on the older scopes, as you change the intensity, you had to kind of twiddle the focus as well to kind of make it sharp. You'll also notice a lot of scopes will have usually a screwdriver control for trace rotation. And that just is changing the tilt of the trace on the scope screen. So we'll say, why don't they just adjust that at the factory? Well, the reason is that sometimes that tilt on the screen, because this beam is steered magnetically, if you move the scope around to a different spot in your room or change its orientation, the Earth's magnetic field can cause that scope, the trace, to tilt one way or the other. Some of the real inexpensive scopes, the trace rotation was literally loosening the CRT and turning it in its housing. Okay, whereas some of the other more, more advanced scopes had actually a trace rotation control. There's another one here called beam find. And what beam find does is, how many of you turned on your scope, you go to use it and there's no trace? Well, is there no trace because I'm not probing the right spot, or I'm not triggering, or the scope is broken, or is it off the screen somewhere? What beam find does is it reduces the deflection voltages, both X and Y, to compress things on the screen so you can kind of see, oh, there's my trace way up there. If I go push the beam find button here on my on this scope, you can see how it just kind of compresses everything down into the center of the screen. So you at least know something's working, the CRT is working, that type of a thing. So it's just a handy thing to say, yeah, my scope's not broken, I just don't have it adjusted right. Okay. But these are all the basic controls for just the display control for the CRT. Okay. Now the next thing we'll talk about is the vertical system. Because one way to think about an oscilloscope is really what it is it's a voltmeter. Right? It's a graphical voltmeter that can plot out voltage versus time. That's really all we're doing. So just like on your voltmeter, you've got settings for AC volts, DC volts, different sensitivity settings for different ranges and things like that. I'm talking about the old analog meters that actually had to switch, not these really easy ones that are just auto ranging for you. Okay, but you actually have controls to do that. So the vertical system on oscilloscope kind of works the same way. We'll talk a little bit about coupling and volts per division, what that means. Now notice the design here. We've basically got an input signal going into a variable attenuator and then into a preamp. Okay? When you adjust the vertical sensitivity on the scope, you're not really adjusting the gain of that front end. Generally, there's a fixed amount of gain essentially from this point forward to drive the scope. What you're adjusting is the level of the signal going into that fixed gain amplifier. Now the reason we do that, it's a lot easier to make a wideband amplifier at a fixed gain and just adjust the amplitude going in, as opposed to developing an amplifier that can be adjusted over 20 to 30 dB and keep it linear over that wide frequency range. Just the same reason we have super heterodyne radios, right? You got everything, all the processing going on in an IF, because you can do everything at a constant IF frequency and just vary what lands in that IF. So we're kind of doing the same thing in a scope, just for gain control and amplitude flatness, regardless of what the vertical setting is. And of course, there are controls for position of where that trace is going to be. And there's a delay line. The reason for that is because we'll trigger the sweep of the scope based on the input signal. And if we just basically kick that sweep off, by the time the signal propagated down to the display, the edge of the signal that triggered it is no longer visible. So what we do is we send that signal through a delay line so you can actually see the edge that you triggered on. So get a little bit of pre-trigger information to see that. Okay. So we're going to talk about trigger in a little bit. Let's look at some of the other controls on the vertical system. And I've got a couple of pictures here of different scopes, because depending on what scope you have, the controls will look a little different. There's typically a volts per division, and that's really the sensitivity control. And this is the adjustment of that vertical attenuator, saying how many volts does it take to move the beam from one division to the next division on the screen. Okay, so if I'm at 1 volt per division, a 2 volt signal coming in will move me 2 divisions. Okay, pretty simple. All right, so you can actually see the scale. A lot of the scopes is going from 2 millivolts per division up to 5 volts per division here. Many of the scopes will have a variable control, because if you turn the variable control all the way one way until it locks, then you're in kind of that calibrated position. If you rotate it off, you'll change the gain, and you won't have a fixed, predictable volts per division. But there may be reasons why you want to do that. You might want to make the signal on your screen a given size for a particular measurement. Now, actually, we're going to do an example of that later on. Many scopes will have coupling or termination controls or coupling controls. So we can, most of the scopes will have a 1 megohm input impedance. That's kind of standard with all scopes. They have a 1 megohm input impedance. But some of the higher bandwidth scopes will also have a switch to give you a 50 ohm termination. It's like we need for RF, and that's the reason why it's there. You also have the ability to take the signal coming in and DC couple it, so that if you put a DC signal on, it's going to shift the trace up or down. And you can also AC couple the signal to remove the DC content and just look at the AC content of the signal. Good for looking at things like ripple on a power supply, for example. We'll do a quick example of that just in a moment. Something else to look at is that all the scopes will list what the scope input impedance is, generally by the connector. And the reason this is important, it says 1 megohm, they all are, but what will vary is the value of capacitance, okay, for that particular scope. Wider bandwidth scopes have a lower shunt capacitance, the slower speed scopes have a larger capacitance. Why do we care? Well, when we start talking about probes, the probes have to be compensated for that capacitance. So when you look for a probe for your scope, you've got to make sure you get one that can cover the input capacitance for the particular scope you want to use it with. So we'll talk about some of these other controls here in a moment, but let's go take a look at this AC and DC coupling example here over on the scope. So if we take a look over at the scope on the display here, I gotta put my glasses on, sorry. So I've got two signals on here. One is a square wave, and one is actually, this channel right here is actually probing the power supply. And if we look right here, that 2 means I've got 2 volts per division. That's on channel 2, and I've also got 2 volts per division on channel 1. So you can see this signal is going, a little over 2 volts, about 2.5 volts of deflection on that little square wave. But then I'm also, if I switch the channel 2 down to ground, you can see there's where ground is on the scope. So I can adjust the position and say there's ground. So if I switch back to DC coupled, I can actually see that's actually the power supply. It's a 5-volt power supply that I'm powering up this circuit with. Now let's say there's some ripple on that. I really can't see it so well. In fact, I'm going to turn off channel 1 to make it clearer. You can see there's a little bit of ripple on that signal. But what if I want to look at that? I'll change the sensitivity of the scope to say 1 volt per division. See, now the signal's up there. I'm starting to see it a little better. I made it more sensitive. But now it's up towards the top of the screen. Let's go down another click. Well, 500 millivolts per division, the trace is up here somewhere, right? So let's take our position control and bring it down. Now I start to see that ripple a little bit better. Let's go one more click down. Now I'm at 200 millivolts a division, but I can't get the signal down anymore. I've run out of range on the position control, okay? So what I can do is switch myself to AC coupling. And now that I'm AC coupled, I can position my signal right here and go even more and more sensitive. And now I can actually see the amount of ripple that's on my power supply here very clearly. So what's interesting is that oftentimes you'll use AC coupling when looking at DC circuits. Okay, so it's not like the voltmeter where you use AC for an AC range or DC for a DC voltage. Here we're just talking about the coupling that we're using to affect a certain measurement. So oftentimes we'll use an AC coupling to look at the small little variation sitting on top of a supply rail. Similarly, we'll often use DC coupling when looking at AC signals. If you're probing through, say, an audio chain in an amplifier, and your audio is getting clipped, if you're AC coupled, you really can't tell why. But if you DC couple through that amplifier, you can see that I'm clipping at the top here because my audio is hitting the supply rail, or it's saturating a transistor. If you're AC coupled, you really can't tell what's going on, but if you're DC coupled, you can see the bias on the transistor as well as the signal. So, like I said, so sometimes we use DC coupling on AC signals and AC coupling on DC signals. So don't think of those as the type of signal you're looking at, but think about what it's doing and how it's coupling the signal into the scope to actually go take a look at. Everybody good on that? Okay. Where did I put my clicker? All right. So vertical modes. Most of these scopes these days have 2 or more channels. How we display those channels are called the vertical modes. So we can turn channel 1 on or off, channel 2 on or off, pretty easy. Then there's these 2 modes called alt and chop. Because even though these scopes have got multiple inputs and multiple channels, and we turn channel 2 back on here again, they're not really 2 separate traces, okay, on the scope. The oscilloscope tube is only producing 1 trace. When you're in the alt mode, what it's doing is sweeping, channel number 1, but the next time it triggers, it sweeps channel number 2. Then it switches back to 1. It alternates back and forth between 1 and 2. It's doing it fast enough that you can't see it. Now, if you're operating at a very slow sweep speed, and we'll just turn this way, way down here, I can actually see that, right? So we're sweeping one channel, sweeping the other one. Okay, that's the alt mode. Okay, let's try this back up here again. Once I start going fast enough, your eye can't see that difference anymore. Okay, the other mode is chop. Now what chop does is during the sweep, it's rotating back and forth between those two signals very quickly. You can't see the change from one to the other, okay? But it's really useful when you go down to these slower sweep speeds, because now both traces will always be there, okay? Now, when you get up to some of the higher sweep speeds, you might actually start to see the chopping happen, and you switch to alt mode, okay? But that's why the two are there. Because there were a couple of scopes that Tektronix made back in the 60s that were actually true dual beam scopes. Actually, we're sending two traces, but the vast majority of oscilloscopes are single beam scopes. So you've got to do some of these little tricks in order to get more than one trace on the screen. Now these little guys here add and invert. Okay, they're here as well. You'll see them here as well. What they're used for is, you might say, well, okay, I've got a signal I'm looking at on channel 1, and another signal I'm looking on channel 2. Adding them doesn't really help me. There might be some instances where adding those traces might be a useful measurement. But what's really useful sometimes is to take the difference between the two. Because that would allow you to measure the voltage across a component. Right? Because with a voltmeter, you can take those two probes, stick them anywhere. Stick them across the resistor, stick them across the transistor, whatever it might be, to see what's going on in that circuit. You can't do that with a scope probe. Because a scope probe has got a single input and a ground. You can't clip the ground in any arbitrary place on the circuit because it's ground, okay? So in order to measure the difference, the voltage difference across a component, you basically connect to either side of the component with two probes. You could invert one channel and then add them. So we're adding channel 1 to the inverse of channel 2, which is the same thing as doing channel 1 minus channel 2. And that's why you've got these add and invert controls, okay? To make a differential measurement across a component or something like that in a circuit. Some of the more modern scopes have got available differential probes to do that right with the probe. But in most cases, this is the way we did it in the old days. Okay? So let's talk a little bit about the horizontal system. The horizontal system is going to be responsible for moving the sweep across the display. Right? Because the vertical system controls sensitivity and everything that's going on vertically. But you got to move that beam across the screen to actually trace out what the waveform is doing. So that's going to basically set the voltage across the horizontal deflection plates to move the trace across. So typically with an analog scope that involves a sweep generator, we're basically generating a ramp voltage. As that ramp voltage goes up, it's moving the beam from one end of the screen to the other. So there's controls for that in terms of how quickly we're going to move it across, called the sweep speed. Okay, we're going to talk about. We'll talk a little bit about trigger hold off, and there's also some modes associated with the horizontal controls. And of course there's a position control here as well. So we've been doing that here on the scope. I just changed my, you can see it says seconds per division right here by the knob. And we speed it up, we can actually start zooming in, actually see the ringing that's going on right on top of that power supply voltage. And all we're doing is moving that beam faster, so we're stretching that waveform out so you can see those details. Now, when it comes to talking about sweep, there's really kind of two types of analog scopes. And I mentioned this just a little kind of historically because if you go back to the really old scopes from 40s and 50s and 60s, especially those that you found in like TV shops and things like that, these inexpensive scopes you can get that were called service scopes, or even like an old SM220 station monitor, you got one of those Kenwood station monitors, they're what are called recurrent sweep scopes. Now what that means is the sweep voltage is basically a sawtooth oscillator that is continuously running. It's always just sweeping across. And you can usually tell a recurrent sweep scope because you've got like a frequency vernier as well as a range selector. You can say, I want to sweep at 1 kilohertz, and I can adjust the vernier of it to kind of adjust that sweep speed. It's not calibrated, and it's very difficult to trigger with. We'll talk about trigger in a moment. I would say these days, there's so many lab-grade, engineering-grade oscilloscopes that are available. There's no excuse for you to be using a recurrent sweep scope anymore. Okay, you can pick up a real scope, I should say, a real analog scope, pretty inexpensive these days. So a trigger sweep scope, the sweep will kick off and move that beam across the screen in response to some trigger. So now what that means is we can synchronize our waveforms to the sweep. Whereas if we just had a free-running oscillator here, the waveforms aren't going to be stable on the screen. Let's talk a little about what I mean by that. So, and really when we're going to talk about that, we'll talk about triggering. Triggering is saying, when am I going to sweep that signal across? Okay, when am I going to start that sweep? And ideally, you want to start that at the same location in time on a particular waveform. So each sweep that you get is going to overlay that waveform right on top of the last sweep that you had. And these old analog CRTs need to overwrite a waveform, many times so you can actually visually see it. So it lights up enough of the phosphor for you to actually see the trace on the screen. Now these old recurrent sweep scopes didn't have a trigger because it's just a free running oscillator. They had what was called a sync control. And what all that did was it took a piece of the input signal and jammed it into the oscillator to try to injection lock that horizontal oscillator to some component in your signal. And if you tweaked around with the vernier control and horizontal, and you just tweaked around with the sync amplitude, you can kind of get the waveform to be stable. But nothing was calibrated. It's just a pain in the neck. So I say, yeah, it really is not what you want to use. Okay, a triggered sweep scope, we basically kick off that sweep each time the signal crosses a trigger event that we're going to talk about here in a moment. So this is really what you want to be using these days, is anything with a triggered sweep scope. If you're walking around a Hamfest and you're looking at a scope, how do I know the difference? Like I said, the recurrent sweep scopes will have that horizontal vernier frequency control. They'll also have like a sync selector and sync amplitude controls. You're not going to see that on the triggered sweep scopes. The triggered scopes will have something that says triggering and has some trigger controls we'll talk about here in a moment. So again, look for a triggered sweep scope. They're a lot more useful and a lot easier to use and to get some useful measurements out of. So let's talk about the trigger source and trigger mode. So the trigger source is what signal do we want to look at to synchronize my sweep that's going across? Most times we're looking at the signal we're applying. We're going to take that internal signal that's sitting in the scope that we've coupled in through a probe and take a piece of that and a characteristic of that and trigger on that. Maybe when the voltage crosses a certain threshold or something like that. Okay, so that's what's called the internal trigger. Okay, we're just going to take a signal that's already coming through the vertical section, take a piece of it, and use that to develop our trigger to scoop that trace across. There's also an external trigger on many scopes. There'll be another input. You could use another input on the scope and bring a trigger signal into that, and then have other traces be displayed with respect to that particular trigger signal. That's what external trigger is. There's also a line trigger, and that basically triggers on the line voltage, 60 hertz. So if you're looking at something that is going to be, like you're looking at power supply hum or something like that, that's going to be synchronous to the 60 hertz line voltage, and it's a very small voltage, it might be tough to trigger on, switch to line trigger, and then you can actually go look at it. Another useful place for line trigger is if you're looking at a signal that is not necessarily something you want to trigger on, but you just want to look at wave shapes. A good example of that is when we're looking at the output of a transmitter, looking at your single sideband modulated envelope of your RF signal. You don't necessarily have to trigger on that, you just kind of want to see what that shape looks like. But setting it to line trigger, it's going to trigger at 60 hertz, which is going to eliminate any kind of flicker or anything like that, and you can kind of see your signal, not have to worry about trigger settings at all. There's also this concept of trigger mode. Okay. Now trigger mode, we're going to talk about here in a moment. Most of the scopes will have an auto trigger mode, and it's not what you think. We'll talk about that next slide. Okay. Normal trigger mode is basically what we've been describing. When the input signal satisfies the trigger criteria, we send that trace across. If the trigger conditions aren't met, we don't send a trace at all. That's what normal trigger means. Single would just send a single trace and then wait for another trigger. It won't continually update. Not really useful on the analog scopes unless you have a camera sitting in front of them. Okay? That's why most of these old scopes have got a little groove right here along the top. There are actually scope cameras that clipped onto that. Little Polaroid film packs in the back. And I remember when I got out of school, one of your rites of passage when you got your first job is someone came running up to you with a scope camera, stuck it in your face and took your picture. And it was sitting up, pasted up on the wall in the lab, all curly, black and white Polaroid picture, basically your nose about all the scope camera captured. That's what they did. And then some of the scopes that you'd find in a TV shop also had TV trigger modes to trigger on the horizontal or vertical frames in an analog TV video signal. And just like we had coupling controls for the vertical path, we also can change the coupling going into the trigger circuit. Remove the DC offset by using AC coupling. There's some other things like high frequency reject, noise reject, DC coupling, things like that that are available. I'll give you a little bit of a hint. For most Tektronix scopes, old analog scopes, a lot of these trigger controls are all kind of next to each other. They're all typically like these big lever switches. If you want to just get the scope running and have something displayed, take all those lever switches and bring them all to the top. Okay, that's the kind of trigger. Put you in auto trigger, DC coupled, ready to go, it starts triggering, and you're good to go. So it's a good starting point. These old scopes don't have a reset button. You can't reboot them. That's kind of the auto set, if you will. So what is auto trigger? As I mentioned, it's not what you think. It doesn't automatically set up your trigger settings for you, okay? But what it does do, it's a usability aid. Because as I mentioned, if the scope is sitting there waiting for a trigger, it's not setting the sweep across, so you don't see anything on the screen. Is it broken? If I don't have the scope adjusted right, what's going on? You can't tell, right? What auto trigger does is it's waiting for a trigger. If the trigger event doesn't happen in 50 to 100 milliseconds, depends on the scope, then the scope basically self-triggers. It sends a trace anyway. And what this does is it puts a trace on the screen, okay, even if the trigger settings aren't satisfied. So you can at least see what's going on. Okay, you set up a trigger, now I see a signal, but it's way over here, it's wiggling around, or something's going on. At least you know something's happening. If we look at this guy, this scope is triggered right now. But if I misadjust my trigger settings, I see some traces on the screen, I'm not synchronized. Or if I switch this to normal trigger, I don't see anything. Okay, because the normal trigger is waiting for this trigger event to be satisfied. And if I don't have it adjusted right, and I got a blank screen, I don't know why. Okay, the auto trigger will actually send a trigger internally so I can see what's going on. And then say, oh, well, I don't have something going on here, let me play with my trigger settings. Oh, there we go, now I've got my signal back. So that's what auto trigger is, and now you know what it is. It doesn't automatically set things up for you. So some of the more important controls for triggering are level and slope. Most times, all we're looking for is we're looking at some kind of a waveform on the screen. It could be a sine wave, it could be an audio signal, it could be a square wave, or we're looking at a clock on a microprocessor or data or something like that. So we want to trigger on usually when that voltage crosses through some threshold, either rising up through it or falling down through it. Okay? So whether we're going to trigger on a rising edge of a signal or a falling edge of a signal is determined by the trigger slope. Okay? So here's an example where the trigger slope is up, so we're going to trigger on the rising edge, so you can see we're starting that trace, that signal's on its way up. Okay? Here we're triggering on the negative slope, so the signal's on its way down, crossing through some threshold. And then that threshold is adjustable through the level control. So with it, I got adjusted a little bit positive here, so we can see we're starting kind of a little bit above the baseline, where this knob is turned a little toward the negative, so we're starting the waveform down here. So that's where our threshold is. So if the threshold is here, I'm going to trigger on a positive slope coming through that threshold. That's why the signal's starting right there. Okay? In fact, a good way to look at this here, let me see. Let's take this signal here. I'm going to put this scope up on the display here. This is something easy for me to show you. Let's bring our trigger level down. Boing. Okay, so we can actually see, I got just a sine wave here, right? If I adjust my trigger level, you can see that it actually draws a level on there. See, as I adjust that level, where that trace is starting is where I'm crossing that. And I'm actually triggering on, so my trigger menu here, I'm triggering on the rising edge. Okay, you can see the rising edge right, oh, I'm sorry. Tell me when this thing doesn't come up here. Okay, so here I've got my sine wave here. So I'm triggering on a rising edge, and there's my level, so you can see where the waveform is starting. And if I adjust that level up or down, you can actually see how that waveform is starting at a different spot, because I'm crossing at a different spot. If I switch my slope to the negative, now I'm starting when that signal's coming down through that threshold. Okay, so it's very easy to kind of see how. So those are the two most common controls you're going to use for triggering are level and slope. Oftentimes you don't really care about the slope, you just want to get the level right. Okay, and again, auto trigger will kind of send a trigger if you don't have these things adjusted right, so you see what's going on the screen to give you some aid in terms of setting it up for you. Everybody good so far? No snoring? That's good? Okay. All right, so let's talk a little bit about digital scopes, okay, and what some of the differences are. Remember, the analog scopes where all the controls in the scope are controlling the deflection voltages for vertical and horizontal to steer this beam around as being squirted out from the inside of the end of the scope CRT. That beam is being squirted out and then being steered vertically and horizontally. Okay, so all of our controls are geared towards that. And since that's kind of our paradigm of how we use scopes, we built analog scopes to have similar controls, or excuse me, built digital scopes to have similar controls, but obviously operates very differently. A digital scope essentially is taking a signal that's coming in through the probe and taking pictures of it, sampling it, okay, and storing those sampled voltages into memory. Okay, and then once we got all those samples in memory, we're just essentially using a computer or some kind of a processor to take those numbers and display a waveform. So we're not directly affecting the position of a beam on a CRT. We're basically building an array of data and displaying that data for you in a way that, it looks like the old analog scope, okay? But that's really what's going on. So there's still the front end is very similar. In fact, let's talk a little bit about it. The front end is still very similar. You've got the adjustable input attenuator, some kind of a preamp that's going into now an analog to digital converter. Okay, so that analog to digital converter, just like a voltmeter, is sampling that waveform and essentially creating voltage samples that then get processed. And we're sampling all the time. So now the trigger has a little bit of a different function. Whereas the trigger on an analog scope basically said, this is when I want to kick the stream off. The trigger on a digital scope kind of looks like it's doing the same thing, but really what it's doing is deciding what do I want to put in memory. So I'm looking at all these samples, and if I got some samples that met the threshold or the trigger criteria I've set up, take those samples around that trigger and save those and display those. Because we're sampling all the time, okay? It's just what do we want to display to you? So the trigger is now a little bit different because we are triggering all the time, we got the ability of displaying what was going on before the trigger happened. So it's like kind of like getting some premonition of what led up to that trigger event. Because I'm sampling all the time, and if I told it I want the trigger to be right in the middle of the screen, everything to the left occurred before the trigger was met. Okay? But since we're storing all this stuff kind of in a circular buffer, we can say, okay, I'm storing all this data. Oh, and there I triggered this, grab some more, and display all that. So that's how you get the pre-trigger information. So again, you've got the same basic front end, feeding an ADC. We're processing that data with the trigger, so we can then take the waveform that we're going to capture, stick it in memory, do some more processing on it to display it to you. And do all this fast enough so it looks like an analog scope. Okay? The digital scopes of 20 or 30 years ago didn't do things very quickly, very well. Modern digital scopes are pretty good at replicating the responsiveness and capability of the analog scopes from that standpoint. Something I want to talk about is something called sample rate. How quickly are we going to take those snapshots? That's going to determine how fast of a signal we can look at and some other properties we'll talk about here in a moment. But all the processing is now done on that sampled signal. Okay, everybody digital scope experts now? So let's talk about sample rate and memory depth. These can be confusing topics. Because if you think about it, I'm going to have a certain amount of time that is represented across the screen. And how many samples do I want to put across that time? That's the sample rate. How many times am I going to take a picture of this waveform as its varying? Okay, so that kind of determines our sample rate, or essentially our resolution. How much time do I have from one sample point to the next? Now, a lot of what will drive that is memory. Right? Ideally, I'd want to sample this thing millions of times across the screen so that I get a very faithful representation of that signal. But if I do that, that waveform is going to encompass many, many, many samples. So I got to have a lot of memory to do that. So as you can imagine, waveform memory, sample rate, and the acquisition length or horizontal settings are all related. In fact, it's a very simple relationship. The amount of memory we need to display a waveform is a function of the sample rate and the acquisition length. And remember on the analog scope, how much time we display across the screen is a function of that time per division control. If I set it to millisecond per division, I've got 10 divisions, the screen would show me 10 milliseconds worth of data. We have the same concept here, except on digital scopes we call it horizontal scale. When I'm demonstrating a digital scope to people, I still call it sweep speed, even though there's no sweep in the digital scopes, okay? But it's still the same concept. It's still so many, nanoseconds, microseconds, picoseconds, whatever, per division. But at the end of the day, it really is an acquisition length of what we're putting in memory, okay? So if you want to have a very high resolution for a given horizontal scale, we need to sample very, very quickly, okay? The other thing we got to worry about with sampling is to ensure that we oversample the signal enough to not alias the signal. Who's familiar with what aliasing is? Okay. If you ever watched an old Western on TV, you see the guys, the horses pulling the carriage, and sometimes it looks like the wagon wheels are turning the wrong way, right? That's aliasing. We'll talk about that here in a moment, okay? Now, oftentimes, the scopes will have a lot more memory than they can actually display. Most of these displays are just LCD displays these days, right? So what kind of resolution you can get on an LCD display? 1024 by 768, 1280 by 1024, something like that. So I maybe have 1,000 points across the screen. But I might have a scope that's got 20 million points of memory. How do I do that? So what most of the modern scopes will do is take all of the samples that lie within one display point interval, and then basically plot them on top of each other and do almost like an intensity grade to kind of mimic what the analog scopes did with intensity grading. Right? Because the analog scopes, the brighter the trace is, it's the more times that trace has gotten overwritten, overlaid. That'll make that trace brighter. Infrequent things will be dim, most frequent things will be bright. By doing this, you can kind of get the same effect on a digital scope. Okay. Actually, let me switch back to the scope here for a second, just to kind of point out a lot of the scopes will actually help you out with this. So let's wait till this kind of, there it is, okay. So if we look right here, we can see that I'm using 10,000 points of memory. And at this particular setting of 2 microseconds per division, so I've got 2 microseconds per division, so 20 microseconds across the screen, over 10,000 points. I'm sampling at 500 million samples per second, 500 megasamples per second. If I change my horizontal scale, I hate to say that, change my sweep speed, there we go. Okay, make the sweep speed slower. So now I'm at 10 microseconds a division, or 100 microseconds across the screen. Now I'm only sampling at 100 megasamples per second. If I sweep faster, okay, now I've got 200 nanoseconds per division, or 2 microseconds across the screen. I'm now sampling at 5 gigasample per second. Okay, so you can see how these things are all related. And most of the scopes will actually tell you, and give you a little bit of a hint, somewhere on the screen, what you're actually sampling at. Okay? And why we care about that, we'll talk about in a moment. Again, it comes down to aliasing. These are all issues and problems that exist in digital scopes that don't exist in analog scopes. So some digital scope advantages. One of the things you can actually do is capture a signal in a single shot, then zoom in on it. Because it's a picture, it's a movie that's captured in memory. Right? So now once I capture the data, all those points are there. I can zoom in, I can make measurements and things like that. We can do single shot captures. We can get that pre-trigger information because we can tell it, I want the trigger to be in the middle of the screen or over here, and I can get data leading up to the trigger and data after. You can't do that with an analog scope. You also have many, many different trigger types. We just talked about a simple edge trigger, but now you can do things like pulse width trigger, timeout triggers, logic triggers, all different types of things because we're all just doing processing on samples to evaluate and determine what that trigger condition is. So there's a lot more possibilities to trigger on particular unique events that you might be looking at. We don't really use that much in the ham shack, but it's an advantage that the digital scopes bring. But another big advantage is automatic measurements. Because now I've got these samples in memory, what's the peak-to-peak voltage? Well, I don't have to go counting divisions, okay, to see, okay, I've got 1 volt per division, I'm going 3.5 divisions, so that's 3.5 volts. I can just ask it, give me peak-to-peak voltage, give me RMS voltage, give me rise time, give me fall time. It just does the math, okay, so you can't do that on an analog scope, okay. Even things like frequency counters, that kind of stuff. Even doing things like Fourier transforms to give you the spectral content of the signal coming in. You get these kind of things, almost like a spectrum analyzer functionality, okay, by just taking and doing math on that input waveform to give you these things. So you can do all different types of math on waveforms. Like this screenshot right here, if anybody's watched I think the most recent video I did was on transistor switching times, and this is the waveforms from that. So this is the collector voltage, base drive voltage, drive voltage into the circuit, base voltage, and this is a math waveform that takes these two voltages, subtracts them, and divides them by the input base resistor. So it's actually a plot of base current. Okay, to kind of show that the base current reverses when you shut the transistor off and that type of a thing. That kind of stuff you can do very easily on a digital scope, and you really can't do that on an analog scope. So you get some of this advanced waveform math, Fourier transforms, things like that. So a lot of nice advantages for that. Now what are some of the disadvantages for digital scopes? They made them all sound wonderful, but they can be a pain in the butt. Now a lot of people will complain that, oh, I don't like a digital scope because it's noisy. Like the traces are kind of fuzzy and noisy. The traces look really nice and sharp on my analog scope. And the reason for that is that the digital scope, because it's capturing all these samples, will show you all those samples. Even if you got a very infrequent little blip or glitch or noise spike or something like that, you see them because it's a captured sample point. On an analog scope, if it doesn't happen all the time, it only happens during one sweep, you're not going to exist long enough on the phosphor to light up the phosphor to see it. So it's almost like a natural filter to get rid of those things. So the reality is the digital scopes aren't really noisier than the analog scopes, but they appear to be because of the way they display your data. And that could be a detriment for what you want to do, right? Now aliasing is, like I said, if you're sampling signals at too low of a frequency. And this is that wagon wheel effect, where the wagon wheels turn backwards because whenever the camera captured a screenshot, it captured the wheel in a different position, and it happened to capture it, and it's, the wheel's rotating really fast, but we're sampling it fairly slow. You might capture it in a different spot that makes it look like the wheel's going backwards when you play those frames back together. This is what it looks like graphically. So if our actual input signal is a signal that's moving very fast, this red one that's going here, but if I sample it too slowly with the green samples there, and I connect those dots, the scope is going to show me that lower speed waveform. It's going to alias the signal. Okay, it's basically a mixing process, and this is essentially what can happen. So if I'm looking at an RF signal at a very slow sweep speed, I might see this low frequency signal and say, what the heck is that? It's because you're aliasing the signal because we're not sampling fast enough. What you can do is turn the memory up on the scope. That will increase the sample rate and avoid aliasing, but you have to kind of know that that can happen. Okay, and you'll see that. Another disadvantage for digital scopes, besides them possibly lying to you, is that they can be pricey. So especially if you're going to buy something new, they can be pretty pricey. They can range from a couple of $100 new to hundreds of thousands of dollars new, depending on what you're doing. So, and they also have a lousy XY mode of operation. XY mode is where instead of letting the horizontal portion of the scope drive the sweep, we drive the horizontal position with another input. Okay, there's actually some useful things we could do with that, but digital scopes do it kind of lousy. The analog scopes are a lot better at this. So we'll talk about that application here in a moment too. So everybody good? Analog, digital scopes, advantages, disadvantages, memory? Yes, you have a question?
How are the digital scopes different than the sampling scopes from the 60s?
That's a great question. So the question was, how are the digital scopes that we're talking about here different from the sampling scopes? And they were, back in the 60s we had sampling scopes, so even today we have them. And you might say, well, a digital scope is a sampling scope. Well, the reality is there is a little bit of a difference in nomenclature. The kind of Digital scopes we've been talking about here are what we can call real-time sampling or real-time digitizing scopes, where we're going to sample a waveform so that even with a single shot, we can get a representation of that waveform. Now, another type of scope is called a sampling scope, sometimes called an equivalent time sampling scope, or sometimes a random equivalent time sampling scope. And what that does is it grabs one sample per trigger event. And then next trigger, grab another sample. And then over hundreds or thousands of trigger events, I've captured enough points that if you connect the dots, you can see the waveform. Now, why would I want to do that? Well, what you can do is you would have a very fast sample and hold circuit. So even though this sampler could be running very slow, maybe 10 kilohertz, 100 kilohertz, we're sampling very, very slowly. We're going to very precisely be able to capture a snapshot at an instant in time, like a very high-speed shutter on a camera. And as long as we know the timing relationship between that sample that you capture and the trigger, we can position it in the right spot on the screen. And then over time, you've built up a waveform. So what it did back in the 60s, before we had enough bandwidth to sample at gigasamples per second, and we were looking at very, very fast signals, we just had to make sure that we captured a signal at a precisely known time with respect to the trigger, and then build up the waveform over time. That's called a random equivalent time sampling scope. It relied on the fact that the signals you were looking at were repetitive with respect to the trigger, but it gave you, even in the 60s, multiple gigahertz worth of bandwidth. Okay, and even today, sampling scopes can go into the tens or even hundreds of gigahertz worth of bandwidth, because all you got to do is have a very precise sample and hold that can open and close a shutter and make a measurement with respect to a trigger at a very precise time. So that's a great question. Thank you.
What's the bottom graphic on that?
Well, this bottom one down here.
Yeah, that.
So this is what a waveform would look like if you were aliasing it.
I thought so.
Yeah, because you might say, hey, I'm triggered, but the signal's moving all back and forth because you're doing that undersampling. And so it looks like this randomly moving, untriggered type thing, even though you really are triggered. Okay. So let's talk a little bit about probes, why we use them. Obviously, we've got to connect the signal that we're interested in somehow to the scope. When we're talking about RF signals, oftentimes we're going to come in with just coax off of a sampler or something like that. But when we're talking about probing into a circuit to actually understand or make a measurement to troubleshoot a radio or something like that, we're going to want to get in there with something just like we use probes on a multimeter. Okay? But there are some special probes that we'll use, and we'll talk about why. We want to minimize the loading on the circuit, right? We don't want to affect its operation by touching it and looking at it. So we want probes that don't really load the circuit much or change its operation. So the most common probes that you'll see are what are called 1x and 10x passive probes. We'll talk about these in just a second. Less common but also available are things like active probes. What an active probe is a probe that might have an amplifier right at the probe tip. So when you go down and touch a circuit, you're actually very close to a preamp that's going to take and buffer that signal out to the scope. And they can provide very, very low loading, less than a picofarad in loading capacitance and that type of a thing. They're also available as differential probes and things like that. And there's also some more specialty probes for measuring current or measuring high voltage or other things like that. So there's a lot of different types of active and specialty probes. Well, let's talk just about the things that you'll most likely use, passive 10x and 1x probes. So a 1x probe is nothing more than essentially a direct connection to the scope. So it's basically taking like a piece of coax, sticking a pin on the end of it between the center conductor and ground and making a measurement. Well, I just do that all the time, right? That's easy. Does it do anything to my signal, right? Well, if you think about it, the scope has got an input capacitance of 10, 15, 20 picofarads, right? You're going to have another 10, 15, 20 picofarads per foot of coax. So it's not uncommon for 3 or 4 feet of coax connected to a scope to have an input capacitance of 100 picofarads or more. If you're probing an RF circuit, is it going to like having 100 picofarads sitting on a diode that didn't have 100 picofarads on it before? 100 picofarads at HF frequencies might just be a couple of hundred ohms or less. So it might load down the circuit too much. So 1x probes are really not used very much because of that reason. They're limited in bandwidth and they place a pretty heavy load on the circuit that you're looking at unless it happens to be a very low frequency circuit or a very low impedance circuit. Okay. 99% of the time you're actually going to be using something called a 10x probe. A 10x probe actually isolates the cable capacitance of the probe itself and the scope capacitance from the circuit with a series resistor that happens to be 9 megohms, right? So I've got a 9 megohm resistor sitting out at the probe tip, and I've got 1 megohm at the scope input. So now I've got a 10x voltage divider. So the 10x probe actually attenuates the signal by a factor of 10. So, well, that's bad, but it also presents a much lighter load to the circuit that you're testing. Instead of looking into 1 megohms and 100 picofarads, you're looking into 10 megohms and 10 picofarads. So especially for RF and high-speed circuits, it presents a much lighter load to the circuit that you're testing. So that's why we use them. So this is what they look like. So here's our tip and the ground. Our probe tip and the ground here, okay? And then there's this 9 megohm resistor that's inside the probe tip, and then the 1 megohm input impedance of the scope. But if you think about that, this 9 megohm input resistor and the input capacitance of the scope probe, that's an RC low-pass filter, right? We all know about RC low-pass filters. We're going to start rolling the signal off. So with a typical 10x probe, once you get above 5, 10 kilohertz, that input capacitance starts to dominate the input impedance of the scope. It's not 1 megohm anymore, it's something much less because of the capacitor reactance of that input capacitance. So a 10x probe has another capacitor in parallel with the 9 megohm resistor. So now at low frequencies, we've got a 10x voltage divider between the probe and the input resistance. As the frequency goes up, we have a capacitive voltage divider between this capacitance and that. So at very high frequencies, we're still going to divide by a factor of 10, but it's because these capacitors have a ratio of 10. Okay. Now the key is we have to get this capacitor and this capacitor to have that same 10-to-1 ratio as the resistors. And then all the scopes have got a different amount of input capacitance. Okay, so if we don't have, so we can't just build one probe that matches one scope, it can't be used on another scope. So all the scope probes, passive probes, have a way of adjusting that compensation capacitor so that its capacitance can ratio properly with that particular scope. Okay, and that's called compensating a probe. If you don't properly compensate a probe, the high frequencies or the high frequency content will either be enhanced, being attenuated by less than 10x, or attenuated by more than 10x with respect to the lower frequency content. Okay. So how many of you have looked at your probes and you've seen the little hole that says compensation and said, what's that for? Or you get the probe and the probe came with this little screwdriver, like, what do I use that for? Okay, that's to adjust the compensation of the probe. Let's actually go take a look at that. All right, let's put this down for a second. Reconfigure my probes here. Now on the front of the scope, you'll see oftentimes something that says calibrator or probe compensation. And that's basically a little spot where we can hook a probe up to. Let me turn off this channel, turn off my chop, and let's adjust this signal down. Let's go down to about a millisecond of division or so. Bring that signal up in amplitude, and let's go trigger on that. Let's see, here we go. So there's my square wave signal there. Now this probe is properly compensated. The square wave is perfect. And remember, a square wave has got energy at essentially the fundamental frequency of the square wave itself, but also has energy at higher frequency content, at odd harmonics. And that's what makes the edges fast. The more high frequency, the faster the edges, the more high frequency content there is. So even this like 1 kilohertz square wave has got content out to hundreds of kilohertz or more. But this probe is properly adjusted. Let's look at what happens if I improperly adjust it. See how I rounded those edges off? That capacitor is not properly ratioed to the input capacitance of the scope. If I was measuring a high frequency signal, it would look smaller than it really is because those high frequencies are being attenuated. Let's adjust this the other way. All right, see how if I go the other way, see how it's overshooting a little bit? The high frequency content is being attenuated by less than 10x. And that's why the edges are getting enhanced and the lower frequency content is being settled out. So the lesson is, go compensate your probes. Hook them up to that probe compensator input and adjust that capacitor so that you flatten out and make it look like a perfect square lead. That's probe compensation. Something that's really important if you want accurate measurements, and so many people don't even know what that is. Okay, but it is a kind of an important thing. Everybody good on that? How many people have compensated their probes? Not as many as had scopes. Okay. All right, how about the probe ground? Like I said, unlike a DMM, a multimeter, where you can put the two probes wherever you want, all these probes are essentially single-ended probes with respect to ground. Okay, there are some exceptions. There are some probes, some scopes that are isolated, but the vast majority, all the probe inputs, all these channel inputs are all common ground. So you have to connect to ground and then probe the signal you want to look at with respect to ground. But now that lead length, that probe lead length will affect high frequency signal integrity. Because we're still sampling a bit of that signal and sending it into the scope to go measure it. And for every current that goes in, you got an equal image current that comes back out. If that ground lead is long, that adds some inductance in that ground lead path. That can ring against, because that ground inductance can ring against the input capacitance of the scope, create ringing on your signal, can affect high frequency signal integrity, things like that. So here's actually some scope pictures from a video I did on this topic that shows about a 5-inch ground lead on a high-speed logic signal. And seeing the ringing, that's all due to that ground lead. And if I replace that with a short little ground spring right around the probe tip, so a 1/4-inch length, you can see how I've gotten rid of all that disturbance. So that really wasn't on the signal. It only got measured because the ground lead was too long. Okay. So the higher frequency you go, the more that ground lead matters. Yeah.
What if you remove the ground lead?
If you remove the ground lead, then the ground will either be capacitively coupled through the air or just go through the ground of the scope is plugged in, you got earth, you got a power supply that's powering your circuit, it's grounded. You'll always get that image coming back somewhere, but the worse you make that return path, the more you can affect things. If you don't connect the grounds and you're probing an audio signal, who cares? Right, who cares if you have a couple of nanohenries of inductance, right? If you're probing a signal that's a logic signal with some fast edges, or you're probing an RF signal, then it can matter a lot. What's odd is if you go really high in frequency, then the capacitive coupling through ground will oftentimes be enough to kind of get away with it. But it's still, I just wouldn't believe the amplitude of the results, okay? But the idea is, whenever you can, use the shortest possible ground lead, especially if you're dealing with high frequency signals. Yeah?
Do you ground one probe or all?
You generally want to do them all because each probe is going to have its own ground path returned back to the scope. For low frequencies, you can sometimes get away with just doing one ground, or even taking the ground connection on the scope. If you look here, this is actually a ground terminal right here on this scope. So I'm probing audio signals. I could just take a clip lead from there to my circuit and just probe around. Okay, but you are subject potentially to picking up noise and RF and things like that, depending on the environment that you're in. But again, the higher you go in frequency, the more that ground length matters. Yeah.
Yeah, I think, Alan, what you'll see often is you'll see like an AC ground or an AC power line, artifact
Right.
floating around.
Yeah, you see a signal bouncing up and down. If you go down, oh yeah, that's 60 hertz. Look at that.
Most of it's usually, if you're holding the probe, you'll find out it gets worse because
Oh, yeah.
you're a big fat antenna.
Exactly right.
Up and like all that energy
Yep.
back on the shield, and there you go.
Absolutely. Yeah.
Is there a disadvantage to always using a short?
You can never get hurt by that. Okay, by using a short, it'll always be better. Sometimes it's just less convenient because there isn't maybe there might not be a ground close by to the node that you're probing. Okay. Here I've got to kind of carefully recognize where I'm putting 2 pins onto my board or onto a socket terminal strip or something like that. That's a lot harder than just coming in with one probe. So a lot of it comes down to convenience. So the idea is use the shortest ground lead that's convenient to make your measurement. Okay, is that short enough? Depends. Yeah. Okay. Any other questions? So I mentioned this earlier, XY mode, and this is where maybe one channel drives the vertical position like normal, but another channel drives the horizontal position. So this is kind of the scope equivalent of Etch-a-Sketch. okay, at the two knobs, right, the Etch-a-Sketch. So this is kind of the live scope, kind of equivalent to that. Say, why would I want to do that? Well, there's a number of things you can do. If you apply signals that are exactly the same to the two inputs, it's like taking the Etch-a-Sketch and turning both knobs exactly the same way. What happens? You get a diagonal line, right? If you do them at the same speed but at a different phase, you can get a circle or an ellipse or turn this line the other way. So that's essentially what we're showing up here. The display will show you in phase at the same frequency, 180 degrees out of phase, or different phases of the same frequency. You can kind of get by looking at two inputs of the scope that way. If you move one of the knobs twice as fast as the other one, you can get this two-lobed type of a display. These are called Lissajous patterns. So you can actually make a frequency ratio measurement with an XY mode. You wouldn't want to do it. It's fun to kind of create pictures and educate or entertain the grandkids or something like that. Okay, but that's one thing you can do. Another thing you can do is a curve tracer. I want to do an IV curve of a diode to check the diode or something like that. You can actually drive the diode and measure voltage and current. This little circuit up here is often called an octopus. Take a look on this Google octopus tester. And what it does is it applies a sinusoidal signal to a device under test, and you plot the voltage across it and the current through it, and basically create an IV curve tracer. Okay. If anybody's ever used an old Huntron tracker for doing testing of working in a TV shop or something like that, that's what they did. Okay. But basically, the Huntron tracker was a fancy octopus tester. Okay. And I did a video on that. You can go make your own. And what it's useful for is just a quick check on components. Now, another interesting application is sweeping an IF of a receiver. Let's say I have a sweep generator that's sweeping through 455 kilohertz, maybe plus or minus 50 kilohertz or something like that. And I'm sweeping this frequency coming out of the sweep oscillator. Now, what if I drove the X position of the trace by a voltage that's corresponding to frequency, and I plotted the response? Now I can actually build a display that plots out the filter bandwidth, filter characteristic of the IF. Now if I want to align it, I can adjust the alignment chords and things like that to maximize that. Interesting way of actually tuning and aligning a radio instead of just looking for maximizing a particular signal. So start thinking about things you can do. One of the first things I did with an XY mode, when I was in high school, I picked up a scope from the lab, the electronics lab in the high school, and I had it in my room. And of course, what did I do? I hooked it up to my stereo. So you can actually look at stereo separation of driving left on one channel, right on the other channel, and actually see if in mono you get a diagonal line. In stereo you get this kind of squiggly type of thing because one channel is driving X, one channel is driving Y. So there's a lot of interesting things you can do. Now, as you can imagine, the XY mode on an analog scope works really well because we're just steering that beam around. XY mode on a digital scope, we've got to sample both, and then math, we've got to kind of build this waveform. So it's kind of a dotty, sampley, noisy, ugly thing. Digital scopes don't do XY mode very well, as I mentioned earlier. So how about the layout of the scopes? All these scopes are different, but what you'll find if you look at them and say, well, gee, that's a big sea of knobs, where do I start? The good thing is that they're all generally arranged pretty logically. So like this old scope here, channel 1 controls were all grouped together here, so that's all the channel 1 vertical controls, channel 2 vertical controls, triggering controls, horizontal controls. They're all grouped together. They're not just randomly placed across the screen. Same thing with this, given the scope we're looking at here. So there's my volts per division, coupling controls, vertical mode, vertical position, all grouped together here for channel 1, channel 2. Here's my horizontal controls. So I've got position, I've got my time per division, things like that. Horizontal position here to move the position of the trace back and forth. Triggering controls are all right here. So we talked about how to adjust or how to use the various vertical, horizontal, trigger, display controls. They are all kind of grouped together. So you kind of can attack the problem in terms of setting up the scope in a very logical way. So regardless of the scope, they're all kind of set up that way. Digital scope layouts are typically the same thing. You'll have, sometimes there's fewer buttons because there'll be more things that are controlled by menus, right? Like, hit a button and it brings up a side menu, and then there's buttons for that. But if you're used to using an iPhone these days, you can drive most of the digital scopes as well. I kind of like buttons and knobs, so my digital scope has a lot of buttons and knobs. I like buttons and knobs. Yeah.
I have a little, when I was doing audio work, before I retired, I had a little 10 megahertz audio scope that would fit in your pocket.
Okay.
And had one, and it also had the calibrator on the back.
Oh, nice. Yeah, because nowadays you can buy a small digital scope on a PC card for like $30 on Amazon. Okay, that will get you by for audio and low frequency work if you just want to go play with a scope. So again, there's no excuse if you want to play with a scope to not have one nowadays. There's those little cheap digital one board scopes are not very good, but there's something. It's better than having absolutely nothing. So the question is, analog or digital? Right? Which ones do you really want to use? And there's a lot of answers to that. In many cases, and sometimes most cases, the digital scopes are better. There's a lot of advantages to the digital scopes these days. Automatic measurements can be really handy. You measure frequency or measure amplitude or things like that very, very quickly and easily. Acquire the data into memory, go analyze it, do measurements, study it, export the data, do things with it. Lots of advantages to the digital scopes. They are a little trickier to use because you got to start worrying about things like aliasing and sample rate and all that kind of thing. You take the good with the bad. Now, for things like maybe looking at the RF envelope of a modulated RF signal, like out of a radio, the analog scopes are better, right? So say this is a typical envelope looking at like a single sideband output out of a radio. Inside this fuzzy area is the RF going really fast up and down, right? We can't see it, but we can actually see the extents of it, the amplitude of that signal versus time. The analog scopes do that really well. Now what happens if I've got this sweep speeds going down relatively slow so I can see the audio envelope, okay, from my voice of that modulated signal. If I take my digital scope and I turn the horizontal scale down slow enough to see the audio, what happens to the sample rate? Remember we said if you turn that down, depending on how much memory we're using, that sample rate comes down also. What happens if that sample rate drips down well below the RF carrier frequency? Now you start aliasing it. Well, that stinks, right? So that makes a mess. Also, some of the digital scopes don't do any kind of intensity grading. So which one of these is more fun to look at? Okay. This one that comes from like the old Heathkit station monitor, or the SM220 like I've got at my shack, or a digital scope. And because this is involving a lot of processing, the update rate of this, how quickly it's responding to your voice and things like that, is not going to be like an analog scope is. So for some applications, especially in the ham shack, an analog scope is actually better, which is good because they're cheaper, right? You can find them all over the place now. Okay. So you get faster update rate, no possibility for aliasing, get the intensity grading naturally because of the phosphor, the CRT. So there's a lot of advantages just for ham shack use. Yeah.
So Alan, I've seen in spectrum analyzers where they actually will give you the intensity in color on the waterfall.
Yep.
So I'm assuming we could do the same thing, not sacrifice sampling,
Yeah,
in a digital mode and maybe with color.
Yeah, some analogs or some digital scopes do have a color intensity grading as opposed to a color bit mapping type of a thing like you have on real-time spectrum analyzers and things like that. But the bottom line is the waveforms that are used to basically stack on top of each other and then look through and build that color bitmap, those waveforms are a given length or a given horizontal time base. So the sample rate is still going to be driven by that. So you still have the potential of aliasing, unless you turn the memory up. You turn the memory up, then things get a little sluggish because there's a lot more memory that the thing's dealing with. So even though you do have sometimes this color grading, you'll still have that downside of not properly sampling the signal, or if you are, getting a sluggish enough response that it isn't really giving a live update.
Yeah, I was wondering if you could, because I've seen it on the spectrum analysis
Yep.
waterfall, so I gotta believe we can.
Yeah, the difference in a spectrum analyzer, what's happening there is those are typically looking at capturing spectrums, like hundreds of thousands of spectrums per second. But typically what we're doing, even though it's a high frequency signal, the measurements are made at a lower frequency IF. Typically these real-time analyzers are down converting into an IF, digitizing at a relatively low rate, and then computing spectrums in an overlapped fashion. Okay, where I might take a vector of data, do an FFT on that, and then move over just a little bit and do another FFT. So I get a lot of overlap processing. You really can't get that on a scope. Okay, not to the same extent. We can talk a little bit about it. There are some ways about it, but the run-of-the-mill, most common digital scopes are not going to have that
There's maybe a cost
functionality.
factor.
Exactly.
Yeah.
Plus you have tons of money.
You got lots of money, that's right. Okay, so like I said, analog scopes really very, very useful. I still use my analog scope as much as I use my digital scope on my bench and in my lab. So let's talk a little bit about scopes in the ham shack. And I don't know, we've gone a little over an hour, hour and a half. We usually take a quick little bio break. Do we want to keep going? How's everybody?
Sounds like a good idea.
5-minute break? Then we'll come back and pick up here.